Hi, good evening, everyone, and welcome to KNVTS Amsterdam April webinar. It's a pleasure to have you guys here with us. Unfortunately, we cannot meet at our Pollux location in Amsterdam, but at least this way we can have this interesting, diverse webinars from all over the world. If this is your first time with us, we are the Dutch Association of Maritime Engineers. You can find out more about us on our website, knvts.nl, and by following us on social media. I'm Mariana Candela, by the way, and I'll be your host for tonight. And tonight we are proceeding with the topic of new energy sources. We have a very interesting presentation about wind energy conversion given by Rik van Hemmen. Rik is the president of Martin and Ottaway. I hope I'm not butchering it. A marine consulting firm based in New Jersey in the United States. In the last decade, they have focused on maritime environmental sustainability, and since 2018 are working on the SurfVac technology, which Rik will go into a bit in his presentation tonight. Rik is an engineer and a published author. You may recognize him from some feature articles that we have in our newsletter. If not, maybe check it out and sign up for the newsletter. We are doing things a bit different tonight. We will have 2 moments for questions during the presentation and a final round at the end. So please write your questions in the chat box. I don't know where it is in your screen, but we'll pass it on and hopefully we'll solve all your questions. But enough of introductions and explanations. Let's get into it. Rik, the floor is yours, and enjoy, everyone.
Hello, everybody. This is Rik van Hemmen. I'm talking to you from New Jersey, and I think I'm going to be off the screen so I can show you my presentation. There it is. I show my screen, and I hope you can see it. If somebody in chat maybe can tell me real quick that it's working. Anyway, my presentation is called "The Stone Cold Realities of Wave Energy Conversion." Boy, Mariana and I both misspoke it. But it's wave energy conversion, and it relates to the present state of the art as to what we're trying to achieve here. First, I'd like to go through some definitions, please. And I live in the United States, and these are actual terms that exist in the United States for things that describe Dutch. I won't go through every single one of them, but it's generally related to the competition that existed between the Dutch and the English, especially at the time of New Amsterdam, and since the English language took over in New York, these terms are out there. And the last one I find most interesting, though, and that's called Dutch uncle, because I've never been able to figure out if this is a positive or a negative term. But I'd like you to know that for this particular presentation, I will be Dutch uncling. And what that means is that there are some things with wave energy conversion that we really need to keep in mind to make sure that we don't send ourselves in the weeds and waste incredible amounts of money. First of all, let's kind of get on the same page. I suppose everybody knows this, but I want to go through it quickly so we're on the same page. Also, there's 3 segments. I'll first discuss the general wave energy conversion issues. Then I'll discuss SurfVac, and then we'll go back to the stone cold realities. So reading off the slide, waves are a form of solar energy. Sun makes wind, and wind makes waves, which in turn decay slowly. It has a nice storage characteristic, which is a little different from wind and direct solar. And now as ship people, as maritime engineers, which is the term that Mariana used, and I really like that term because in the United States we say marine engineers, and that doesn't make any sense because that becomes confusing. We could be ship operators, or we could be people dealing with engines, but not necessarily naval architects. Maritime engineers, ship people, they say that they feel that waves are an unavoidable nuisance. We live with them. I suspect, in theory, we'd like to have as few waves as possible, even. And we know that as ship people, waves are unpredictable in detail. And what I mean by that is that we can talk about a certain wave height, but we all know that it's not one particular wave height. The world is not nice and smooth in waves. We have to deal with spectra, and we have to deal with rogue waves and all kinds of unusual characteristics. Now, on average, waves are highly predictable today, and this is actually a powerful use for the wave energy conversion industry, both to say, well, what kind of loads do we have to deal with in general in various locations, but also with regards as to predicting what type of energy we can extract in certain locations. But dealing with waves is really difficult. And it's mostly because they really have a lot of energy. I mean, they're very dense energy packages, and that is very nice from a energy delivery point of view. But it's a little difficult in with regard to an energy extraction point of view. So, but because it's sustainable energy, we want to extract it today. I mean, it's very important that we want to extract it, and this is sort of my holy grail. This is what I call the sustainable energy triad. And the remarkable thing is, and quite frankly, here I'm talking about, and I was showing a picture of an island, and the cutting edge of true sustainable energy is very much related to getting this to work on smaller islands. And for example, I'm rather deeply involved with the island of Barbados, which really has a very aggressive program on trying to become energy independent. And that's interesting because they're very small islands that are being that are almost energy independent, for example, in the north of Scotland in the Faroes. But Barbados is now a larger island, and it has more roads and infrastructure and tourists and hotels. And they are looking at becoming energy independent. And really the only way you can pull it off is to have a combination of solar, wind, and waves, and some level of storage or backup power. And if we get this to work on these larger islands, the pieces are really starting to work out nicely. The trick is, the advantage of the energy triad is that when the wind's not blowing, there might be waves or the sun might be shining, and between those three systems, you should actually be able to reduce your storage in the system. And storage is the part that doesn't really make any money. When you generate energy, you can sell it, but the storing is actually what takes the profit out of your production. The interesting thing is that this program is closely associated with the United Nations. And the interesting thing is that the United Nations works with something called Sustainable Development Goals. And these are all kinds of goals they've set to provide a sustainable Earth. And they are sometimes social, like education, and sometimes they're like pure global, like climate action. The interesting thing that I find about these sustainable development goals is that all these goals, or definitely the vast majority, probably all of them, actually make headway simply by building sustainable energy. In other words, if you have sustainable energy, you will be able to build industry innovation infrastructure, because you have energy that's sustainable. You can use that energy to build things, or to even, God forbid, make cement, which is a carbon dioxide emitter too. But it allows you to have sustainable cities. It reduces CO2. The sustainable energy, it doesn't have any pollutant impact, so it helps the environment. It works all together. It's really the lead issue of our time. And wave energy is a real big deal of it, because there is so much of it. So as engineers, we want to engage this, and we go, well, there has to be some way to extract that energy. And as engineers, say, how hard can it be? And furthermore, as engineers, we build all kinds of structures in the ocean. So while we think it can be done, if we are experienced engineers, we also know that it's not easy. But we've had offshore oil platforms in some really nasty oceans, especially in North Sea in the 60s, and other places that eventually became even more aggressive. And we've moored all kinds of stuff in the oceans. And really the thinking has been, well, we clip some thingy on there and extract the wave energy, which is then banging into these fixed structures. And we'll call it wave energy conversion, WEC or WEC. That's the term I'm starting to live with pretty much today. When I first started looking into wave energy conversion, there were literally dozens of different acronyms for it. But I'm promoting WEC here in this particular presentation. So in that thinking, we go, well, we got Condeep, which is this huge concrete structure that is made to sit out in the middle of the North Atlantic. So we could put a thingy to it, clip something to it, and then we get wave energy conversion. And that works, but then from an engineering point of view, there's all kinds of things that take place. One is that, well, it's a drag device, and we actually design the offshore structures for low drag. And then that brings in an entirely different structural approach. And then if you start to think a little harder, we go, well, yeah, we can capture all the waves around Condeep, but that actually doesn't add up to that much energy. I mean, we're going to pick up some energy and maybe you can keep the lights on at Condeep, but it really is not. We don't want to build hundreds of Condeeps to simply get to utility level wave energy conversion. And when you do that, it gets to be very expensive. But still, we should try stuff, and we've been trying stuff. And modern efforts have been made since the 60s. When I started this wave energy conversion thing, we looked at what had been done, and we found over 30 deployed efforts. But the overall results have been, well, actually, they were very disappointing until about 2 years ago. There's been some progress, but there were some real failures there. And now there's been some solid engineering, but there's also been stuff that simply doesn't make any sense, and it leaves one wondering where the money comes from to build something that doesn't make any sense. The largest producers have all been below 1 megawatt, and you really need to have 1 megawatt units to be able to get to commercially viable energy production. Even PV solar, we're talking about 1 megawatt solar generators in fields and stuff. When we're dealing with commercial energy, our rooftop solar, which I have some too, and I love it, is not commercially viable, even though it does contribute to the overall game and sometimes to a large extent. In Europe, people think of the United States as not being particularly interested in sustainable energy, but that is not entirely true. The United States is like Europe. It's a whole bunch of different states, and some states are into it and some are not. For example, in New Jersey, we have a relatively high percentage of rooftop solar acceptance, and the economics are quite good for it. Now, so far, there's no viable effort of producing utility level power, and we need utility level power. Anything less than that is simply not going to do it. And the only commercially available WEC is for boutique applications. So I'll go through a couple of things that are out there, and here the Dutch uncle part really comes into play. This is a concept called wave sub. It's actually been deployed off England. It has had an investment of probably close to $100 million. What it does is, even though the two units don't look alike, one is the concept as to what needs to be done on the right. On the left is, let me see, I got a cursor here and I got a cursor here. On the left is the actual deployed device. Now that the lower part of the device sinks, and that bubble, the ball over there, would then be subsurface similar to this. The one on the right has some interesting features that I'll talk about in a minute, but let's talk about the concept first. This device sits below the waves, so we know as engineers that it is neutral buoyancy. So the only reaction that the wave has on this particular device is drag. So the rotational energy of a wave comes through and it makes that thing go back and forth, and that is going to actuate these levers. And I suspect, even though nobody has provided me details on it, that there are hydraulic cylinders in there or hydraulic pumps that allow hydraulic fluid to be pumped in a reservoir, which can then generate energy. The thing that really bugs me about this particular design is that they are capturing or trying to recover energy from waves in a submerged fashion. You cannot efficiently do that. The reason you can't efficiently do that is the same reason that the submarine doesn't stop ocean waves either. The measure of the recovery of your energy is related to the amount of wave you basically kill off. And if you have a submerged device like that, you're not killing anything in a wave off. And the reason for it is that it doesn't suppress the wave from a buoyancy point of view. It suppresses the wave from a drag point of view. That's only that much in the entire wave energy column. As such, it is not inherently a device that will be effective. And if anybody runs the math on this, it will become immediately apparent that even though you can get it to work, you're not going to make any money with it. Now, the realities of wave energy conversion are frustrating. This is a device, it's a 7.2 kilowatt peak device by Ocean Power Technologies, which is also a New Jersey company. And this device is actually commercially available. And they've, again, spent a lot of money getting it to work. And I'm sure there's some really good engineering that's gone into it. The only problem is that this device generates 7.2 kilowatt at peak. Now, peak is the nameplate capacity unit, but a wave energy converter, just like a windmill or a solar panel for that matter, has a nameplate rating, and it also has an actual production that it actually produces. But let's just assume that this unit always produces 7.2 kilowatt peak. The frustrating part about that is that if you go over here and look at the semi-trailer, at the tractor trailer that's towing it, the engine at a tractor trailer is probably about 300 horsepower, so that would be in the 250 kilowatt range or 220 kilowatt range. So basically, a device here that needs to be towed by a truck that has an engine that is orders of magnitude larger than the actual energy that can be generated by that device. That inherently shows that this is not the way to recover utility level energy. If you were to put many of these units out, you would be paying a fortune, and you wouldn't be making any money with it. So just for comparison, and some of you might have seen some stuff on this already, but for comparison, 7.2 kilowatt peak, this particular boat is a 35-foot boat that I'm building, and some of you might have seen a reference to it. This one has 4 kilowatt PV solar on the roof. So those panels over there, which is basically stuff you buy off the shelf, 2 sets of those is going to beat this particular unit over here. There's other engineering that's going into this, and some people worked at it very long. This is the Fred Olsen Bolt C-Power. And the reason that I'm impressed with this unit is because it's an anchored unit that has these devices over here, winch devices, or rather traction devices, probably a better word, that have wires that go to the ocean bottom. And when the waves make this unit move, it extracts energy. That is really difficult to engineer. And apparently Fred Olsen has engineered this. Now, I'm particularly interested in it because when we go on, you'll see that this is something that applies to SurfWack too, and we'll go from there. So this is it's called ocean energy, the term, which I find a little problematic, but that's what the unit is called. It is a air-driven device. So it's a large device, and a wave passes through it. It changes the air pressure in a chamber, in an enclosed chamber, and that helps generate energy. Again, this device is interesting because there apparently is a 1 megawatt unit that is now either being tested or is ready to be tested off Hawaii. It's a very large unit, and it will generate energy, but the question is, can it do economically? And the reason I'm asking that is because this thing should work really well in big waves, but when it's smoother, when waves are not that big, it is unlikely that the compressibility of the air inside the chamber actually will be able to generate any real energy when there's small waves. This is one that I like also. It's called Wave Roller, and this actually is a 1 megawatt unit, and it's actually been deployed, although I haven't seen the returns on it yet. It's been deployed, and it's basically, I like to call it the flippy flopper. It has this particular unit on there that sits on a hinge bar, and it flops back and forth into ocean waves, and then it has a hydraulic system here that drives that drives accumulators and then again generators. This is a human here, so it shows you the scale. Again, this is 1 megawatt, so that's 1,000 kilowatt. So it's a 1,200 horsepower engine. Again, the engine for the tug, that's probably around 1,200 horsepower, is buried somewhere in there. Again, these scale issues are a problem. And if this thing were actually generating 1 megawatt all the time, it probably would be able to come close to economic viability. but it will not necessarily do that. For example, it's being deployed right now in a nearly calm ocean. So this is the point where I'd like to entertain some questions, if there are any. Mariana, are there any questions?
Sorry, Rik. No questions
Okay.
to this moment.
Well,
I
that
think we
means
can
we
continue.
either have a knowledgeable audience or I put everybody to sleep, but I'll go on.
Hopefully not.
I now go into the next part of my presentation. A man, that's me, walks into a SNAME meeting. It's the Society of Naval Architects and Marine Engineers. And it was New York City around 2010. I actually never bothered to really figure out, to go back in the record to find exactly what it was. But there was a gentleman by the name of Mike Raftery. He was there and he was doing a presentation on wave energy conversion. And this is just like your Royal Society meetings. You know, it used to be where we got something to eat and then there'd be a meeting after dinner and questions. I at that time was already interested in wave energy conversion. But when he started making his presentation, I realized it was different. And he had an interesting idea. And really the point he was making is, let's get the ways where we can extract the most energy. And strangely, we all kind of intuitively know where we can extract the most energy, because that is at the beach where the waves are coming in as surf. I mean, surf will knock you off your feet. While if you swim past the surf line and get in the middle of the ocean, you can happily float on your back and there's nothing going on. That is really the interpretation of wave energy conversion. You have to find a spot where you put the most energy in. And he felt that surfing waves would be most useful, but to put it in the surf doesn't work. And there's a number of reasons why it doesn't work in the surf. When you have a really bad storm, you can't get out of the way. And when you have tidal changes, the surf height changes, and then it doesn't suit it right. And what he said, let's devise a shoaling feature to create cresting waves. And cresting waves are the intermediate stage between breaking waves and ocean waves. I thought it was really clever, but I was busy and I forgot about it for 8 years or so. But this is what Mike was talking about. This was actually done in the Stevens Model Basin in New Jersey. And so you have a wave where a certain height is happily rolling into the ocean. And then it comes to this base that is submerged and at a certain distance. When it gets to that base, the wave starts, because it's basically a wave that feels the bottom, which is why waves crest and waves turn into surf. It's starting to feel the bottom and it becomes steeper. And when it becomes steeper, it gives you, it also slows down in its wave speed, by the way. But when it becomes steeper, after it comes past this base, it actually starts to transition back to a normal ocean wave again. Only a small amount of energy has been taken out. And what Mike was thinking is, when I'm sitting over here, when I have this nice steep wave slope that people normally surf on even, then if I have a point absorber there, then I can really pull some stuff out of there. And he went on to think about that. I mean, that's the reason why we surf, right? And he came up with this device. So this is the base, and this is what I have officially called the bobber after I got involved in this. And a wave comes through. The wave starts to crest or break, and it yanks this thing back and forth. And meanwhile, this unit is anchored on the seafloor, and if the waves become smaller, it gets brought up a little bit, and it still allows that wave to crest as steeply as possible. And the wave gets bigger, it goes down a little bit, and it again allows this wave to crest as steep as possible. Now, and when I say this wave, we have to keep in mind we're dealing with spectra, so it gets real fuzzy. And whenever it gets real fuzzy, what's really fun is to apply neural network control systems that learn and get that to work as well as you can. Now, Mike did a lot of work on this, and he even got a patent on it. And the one thing that actually kind of came up was interesting is that Mike said, well, here we have a 6 megawatt unit. And in that unit, we have these ropes that pull on these hydraulic motors. And they pull on these motors and they pump hydraulic oil into reservoirs, which are these cylinders. These are air hydraulic reservoirs. So they're filled with air, with a membrane, and you put the hydraulic oil in, compresses the air. and then you can, when you have enough of that stuff stored in there, you can run it into these generators, and then you can basically send the electricity to shore. What is interesting about this is, and that's something that it doesn't really occur with wind energy and with PV, is that there's a built-in storage device, and that's very interesting from a utility point of view, because utilities are very interested in buying chunks of energy. So if you can basically send a signal utility and says, well, I have 6 megawatt hour of energy stored and available for you, the utility says, I'll buy it. And then they'll bring it out and put it online. And then the production can go on at least for that block, but it will probably go on much longer because the energy of the waves has come in, and waves last a long time. That level of predictability is very attractive to utilities, and Mike felt that this needed to be built in very quickly, and he did. These winches, they are all powered, and they go in and out, and it's not a very complex system, really. This speed is not a very high speed system. You can adjust it, in meters per minute. But this thing is different. These winches, they get yanked back and forth like you wouldn't believe. And as an engineer, that's the part that had me very paranoid. And this goes back to that bolt, Fred Olsen bolt system, which actually has done that. But it was much smaller, but they've managed to do that. And so this is where these technologies need to be transferred and integrated with each other to get the things to really work really well, rather than to focus on our own little game. Other interesting part of this system is that actually Siemens developed this system. It exists. These motors and this storage cylinder concept was developed by Siemens for a hybrid garbage truck. And garbage trucks stop and start all the time. And they felt that they could use regenerative braking through a hydraulic motor to go into a hydraulic storage system, which can then provide acceleration again to the truck to make it move. So the system was not off the shelf, but it had been prototyped and developed and everything. So Mike was quite far along, but he was also stalled in the whole project, and he had lost support of Stevens. But this is one of his later tests, which shows the bobber and the base, and I'll run that real quick. And this is where the spectrum starts to come in. The wave maker starts, and there it goes. And the cool thing is you can see that lower platform go in one direction, and in the up and the bobber go in the other direction. And what it really comes down to it is you want to use buoyancy, which is the most powerful force in ships, not drag, because drag is always a small portion of your buoyancy forces. You want to use the buoyancy forces to generate the energy out of the steepest possible waves, and this is what it's doing. And there's one that's making some money. That one is putting the kids through college. That's how you generate energy. So it kind of repeats, but there you go. So what happens was, through a weird set of circumstances, I reconnected with Mike Rafter in 2018, and I was still interested. I mean, somebody reintroduced me to the concept. So yeah, that's really where it needs to go. So Mike and I actually hid out for a couple of days, and I said, show me everything you got, and turned it inside out. And he has worked out his numbers. Mike is very hardcore, but really I only wanted to look at this as economic viability. And when we started to run those numbers, they look pretty good. And we decided to start Surfwake. In other words, we were not interested in science projects. We were interested in the solution that's going to provide utility level power. So we make some improvements to the concept. This is a later concept. It's now a 4-cable unit, and it's round, and it's unidirectional. Again, here's the animation of it. Now, this is kind of fun. I said, well, I'll put a human with it so we can see what scale it is. And this was the die, but that didn't work. So then I asked the animator to put a whale with it. So this is sort of the scale that you're looking at. What's kind of interesting too is, and I'll run it again, is that people sometimes worry about whether animals get stuck in these things, and undoubtedly they can, but it needs to be remembered that all of this moves at the speed of waves. So this environment is really not more dangerous than, say, a rocky shore. And as such, you can pretty much expect animals to have a certain awareness of it. Hang on, I hit the wrong button. Come on, gotta move. All the time. Okay, so and I was very much interested in the economic evaluation of this stuff. And this is an interesting graph. This is the levelized cost of energy, which is a sort of an industry accepted way of analyzing how much energy costs from a planning and mostly from a planning point of view. And the world is a very interesting place, and we have to remember that is that and when we started, I'm picking coal here. Coal is the purple one. If you look at the price of coal, it was up here about, this is in 2010, this is what you paid for coal. And people go, well, solar PV will never work because it's so much more expensive. Well, the really interesting thing is, like, there we go, went all the way down, and solar is now fully competitive with other things, and such as onshore wind and gas. The one thing that is not quite there yet is the light blue one. That's the one on top, which is offshore wind. Offshore wind is very expensive still, but still we are investing in offshore wind, and we're doing that for a number of different reasons. One of it is that if we can get it to work, first of all, on large scale, the cost will go down, and if you make windmills bigger, progressively bigger, there's still a bit of headway to be made. This is the cost for offshore wind of New Jersey, and what has happened is New Jersey is going to fund offshore wind under this price, which personally I think is not a good deal. It should be, we will fund the first pile of offshore wind like this, and then we go down, and the next pile of offshore wind gets funded like this, and meanwhile that curve keeps going down, and commercial operators will keep stepping up. But that will get sorted out as time goes on. The interesting part is this red bar. When we do a reasonable levelized cost of energy analysis, it turns out that the SURF-WEC concept sits right here. And you might ask, well, where are the other WECs? The other WECs are not even on this graph. They're not even on here. They're way up there. Now, why is that? And the reason for it is that it's almost an order of magnitude less expensive, because a SURF-WEC can extract more energy, and it can do it over a much longer period of time than conventional wave systems, because it tunes the waves. And that's really the simplest explanation for it. It's just one of those things, when you get in a beneficial cycle, everything goes your way. And if you get in a vicious cycle, nothing goes your way. And in this particular case, it looks commercially very attractive. What it also means is if you don't tune your waves, you'll be up here, and you cannot get any closer, because the bigger you make your device, even if you might have a device that works at this rate for a small device, you need to make your device bigger to go down this curve. The bigger you make your device, the lower is the amount of energy you take out per day, or per year for that matter, because the device doesn't harvest small waves. So in conventional devices, you can put out a ton of small devices, which are inherently expensive, or you can put out a couple of bigger devices, but they are not inherently as capable of harvesting every wave that's out there. If you tune the waves like SURF-WEC, you can actually pull that off. So I already kind of jumped the gun there a little bit, but this is what it comes down to. And small waves become steep waves. And by the way, it isn't just that the waves become bigger, it's also becomes steeper, which again enables you to take more energy out of the system. And then one size fits a lot of locations, which is really interesting. Using this SURF-WEC concept, we set a standard size of about 150 feet by 150 feet, and I think it's now more like an 8 megawatt unit rather than a 6 megawatt. But again, that's nameplate. But you can one of these units fits a lot of locations. It is very little need to say, well, I have a lot of big waves, so I need to have a big unit, or I have a lot of small waves, so I need smaller units. One size fits all. Now, the other thing that's interesting too, which adds to the energy conversion ability, is that offshore is where the energy is. Believe it or not, even though these surfing waves come on the beach, they have lost a lot of the energy from the ocean waves simply by sensing the bottom over relatively long distances. And then directionality is a factor. If you have something that cannot turn into the waves in the most effective fashion, you have a unit that might not be doing anything for a period of time. And when the waves get really big, you can detune the system, and that means you can actually make the whole system basically just disappear on the water and not have it exposed to the really big waves. But having said all that, when you put these pieces together, we're talking about an order of magnitude higher usage factor than most systems, a higher order of magnitude of higher production per dollar equipment spent. So keep in mind that buoyancy and motion are the drivers for wave energy, as I showed. Drag forces are always a fraction of buoyancy forces. And then neural networks are natural for wave energy conversion, which is fun because there are many things that could not really be accomplished without neural networks, and wave energy conversion is one of those. But we can probably pull it off with neural networks to an extent that we couldn't before. Now, installation cost is a significant factor, and that goes back to the various devices I showed you above. And maintenance cost is a very significant factor. And both in SurfWack it fits pretty well in that category. It's 130 feet deployment is not a big deal. You can still dive if you have to, but you probably don't have to. And maintenance cost is related to having a unit that is big but not too big. That sounds weird, but it's the truth. And then environmental impact is an issue, and you want to find devices or design devices that can take advantage of the production cost curve. So again, we at SurfWack, we very much push and say design power plants, not home projects. And so in 1 year, this offshore plant, if you look at that picture, can produce the same amount of energy as a decommissioned power plant, which is actually over there. So this is 1 megawatt, 1,000 megawatt production field that has a shore connect to the red line, and that basically ties into this 619 megawatt nuclear power plant, which has just been decommissioned. By the way, this is the coast of New Jersey. I live in this particular area. And again, New Jersey is really trying as hard as many of the European countries in trying to hit sustainability, and that is being done in New Jersey by investing in offshore wind. Well, if you're investing in offshore wind, it certainly makes sense to also plan for offshore waves, and that really means that if you co-locate these offshore wind with offshore waves, you get an even better cost picture. That's not just for SurfWack, that is also for all wave energy conversion. Co-locating with offshore wind makes sense. Strangely, the industry, or rather I should say the government, hasn't really thought their way through it. They're asking wind farm companies to put out wind farm projects, but they should really say, well, since you get these leases anyway, make sure that when the wave energy conversion kicks in, that you have an offshore connector capacity to make it all work together. So again, just for scale, this would be 24 miles offshore. It'd be 10 miles long. These white rectangles are called quads, and they are the lease areas that you can actually get from the U.S. From the U.S. Bureau of Mining to exploit energy from those units. And then this whole thing is 10 miles long. There's 200 SurfWack units in that. They're 150 feet each. They're not located all in one line. They're staggered in some kind of complex pattern. So let's talk stone cold realities, but if you have questions first, I appreciate it. And I mean, I appreciate it.
Hey, Rik, we have a couple of questions already.
Okay.
Two that we can maybe combine are about maintenance costs. So Hubert Mertens and Robert Rudolph Schreiland are asking, compared to wind energy, how is the maintenance cost of this system, and in regard, because Hubert says that it is pretty close to the surface, so how about the marine growth and corrosion?
Yeah.
And
okay.
And also, Robert is asking if the unit needs to be towed somewhere.
Towed, yes. I'll stick to this picture. It's kind of fun. If you have 200 of these units, and we design them to a sort of a class cycle, 4 or 5 years, when you take them in, and then when you take them in, you service all the equipment and all these things, and then they're supposed to go out again. First of all, as compared to offshore wind, as near as we can project, it's about the same but different. And the same and different is related to the fact that once you have offshore wind planted, really it's very difficult once you have offshore wind planted to bring it in. But in this equipment, if you once it's planted, and I'll go back up here, once it's planted, it's not so difficult. You know all this is shore controlled, and so you say to them, oh, actually this one I skipped, but this is the, let me run this while I mention it. This is the storm avoidance system. So really what happens, you bring the platform down, and now you're no longer creating shoaling waves or cresting waves. And when it gets really bad, you can actually sink the bobbard too, and then you have the kind of system that I showed in the earlier one. It's nowhere near as efficient, but in these huge waves, it would certainly generate energy as needed. But as far as maintenance is concerned, just like this thing can go down, you can send it up too. You can make the whole thing surface. The whole thing is surfaced, and the bobber sits right on top of that unit. These anchors, you can either leave them, they're suction anchors, or you can actually release them in this 4 or 5 year cycle. Then you can take them in, you put them in dry dock, and you get rid of the growth. Now, the growth thing is really interesting because keep in mind, this is a device that actually loves drag. I mean, you want to add drag to it if you can. So it's not like it has to be painted anti-fouling. We don't care if it gets a beard. It would simply make this thing follow the wave pattern more and allow it to extract more energy. So that's a real kind of fun part of it. You surface the unit, you hook up a tow, you tow it into a dry dock, and you take all that organic material off, and you use it, I don't know, for cement as far as the barnacles are concerned, and biofuel as far as the kelp and the weeds is concerned. And you clean it up, and you take it out again, and you service it. The coating would actually be like a high build epoxy. It doesn't matter that you have no anti-fouling on it. So from a maintenance point of view, it kind of becomes part of the cycle. You have 200 units out there. You have a dedicated crew that pulls these units out on a schedule. So 200 weeks, so one a week, and takes it in. And while the other one is being cleaned, and it could take 3 weeks if you have 2 spares or 3 spares, and you place the next one, and you just keep going through that system. So it's a continuous maintenance system. And from a cost point of view, it is similar to offshore wind because the offshore work is very limited. You don't have to do a lot of offshore work. Well, with offshore wind, you spend a large amount of time offshore, which is inherently expensive. I think I kind of got to the answer on that. Is that correct?
Yeah, well, at least it's for me.
Yeah, go ahead and follow up. Somebody, if I didn't answer, please feel free to beat up on me. Next question.
Do we have another? Okay, we do have from Rafael. You know him. He asks if any intact stability check was done for SURFAC.
Intact stability, is that what I heard?
Yeah.
Okay. Yeah, this is if you talk about a floating stability point of view, it means next to nothing. If Rafael is asking when this thing is moving in big waves, if it could flip in upside down or inside out, it is not. It's not a big deal. It won't. And again, this comes down to wave avoidance. When things get bad, this thing can sink. So it sort of covers it. There are really interesting hydrodynamic effects that are taking place here, and that is that that resonance type behavior that you see there. That in theory you could analyze that. The funny part is in practice, if you run it as a neural network, you don't have to. You simply let that neural network learn until it is extracting maximum energy. So in other words, these hydraulic these hydraulics, they throttle depending on what kind of wave is coming through to give that to give the bobber as much motion as possible without it stalling, and provide enough of a jerk to the base that the base flies in the same direction. But then when the bobber comes back, that it can actually catch that base on the reversal of its direction. So it's kind of a fun project. If you look at the video of the tank test again, you kind of see how that comes together. Any other questions?
About fatigue from Simon Stoutner.
Right.
Especially of the equipment which are due to all the movements. Is it possible to ensure that these are capable and fit for purpose for the entire design life of approximately 5 years?
Right. This is why I'm telling you that I have cold sweats about that that wire system, and I have a backup. You'll see it in a minute, but that wire system is scary. I'm not worried about the hydraulic motors. That is fine, but those wires are a big deal. And believe it or not, we're looking with Langhorst ropes at this, and actually rope fatigue is its own class of fatigue. Structurally, there are not many things that I would worry about from fatigue. Keep in mind that ships are designed for 5 years fatigue life, at least, right? And so as far as the overall structure is concerned, it's no different from ships moving in waves. So that is not really the biggest deal. The big deal is those ropes that are being yanked back and forth on these drums that are connected to the hydraulic winches. Now, there are interesting things in that too, because again, in a neural network, you should be able to put in control factors that say, well, I don't want certain peak loads in my ropes. I'd rather have that thing simply walk away without recovering energy than have the ropes yanked off. So we'll know a lot more when we get to the prototype stage. But from an engineering point of view, there's a lot of I should put fallback positions. There's another thing that's interesting to remember too, which we don't always think. And when I first looked at it, and go, well, what about the pressure? It's 130 feet. What about pressure and stuff? This lower unit is ambient pressure. It is either ballasted, which is uncompressible, or the compartments have equipment in it. Because there's no humans in them, you can simply pressurize them. So when this thing sits at 10 feet, the unit is basically neutrally loaded as far as hydrostatic pressure is concerned.
And what about the mooring system? What do you think, as a naval architect, is the biggest difficulty in terms of mooring?
Yeah, it's interesting because this mooring system is not terribly weight constrained. Very often when you think in terms of mooring systems, you go, well, what's the weight problem, right? This is 130 feet. So if necessary, if I say, well, I'm really don't want to get tricky or anything, I can put it on a cogged anchor chain and just clink it in and clink it out. We could again do it with artificial fiber and work that out too. But we've moored to chain for many years, and so that shouldn't be a problem by itself.
Okay. Now, a fun question, I would say, about operation from Marius Dam. How do you prevent ships running into the floater?
The same way you prevent ships from running into anything else, offshore wind or these things. That keep in mind, this thing is up, this thing is surfaced, and there's actually a little box there that has a beacon, and it also has an additional transponder that allows signals to go to the base acoustically if there's any problems. But it's simply something that's on the chart, and it's whether it's a buoy or whether it is an offshore light or things like that. It is available and visible. The interesting part is that undoubtedly somebody will run into it. I was involved a number of years ago with Texas Tower, which is basically a jacket structure that was offshore. It's called the Ambrose Light. It was the main approach light for New York City, and it's been there for 30 years. But somebody decided to run into it, and drive right through it with a large commercial vessel. So it was a 4-legged tower and it became a 3-legged tower. So these things will happen, but they are no different from other typical marine obstructions.
Okay. So a challenge for you, maybe?
I love challenges.
From from Victor Condotti. He says that towing the barge back to harbor might be easy, but we are talking about 100 of these for a full developed farm. In a wind farm, service vessels can reach multiple turbines for one outing. What do you say about that?
Well, it depends, and the reason it depends is that if for offshore wind, I agree, but with offshore wind, for example, they've had terrible problems with reliability of the generators, and that is apparently occurs due to whole body vibration. And when you have a generator problem, you're going to spend a hell of a lot more time than a couple of hours at one of these units. It gets to be a real difficult game, which also requires safe conditions as far as wind and waves goes. And when all that is said and done, there's nothing easy about it. Moving tugs and barges, I'm sorry, but the United States is a tug and barge business. We do tug and barges because actual ships end up being very expensive on the Coast Guard requirements because they require very large crews. But if you were to tell a tug and barge operator that you get to go offshore 10 miles, raise a barge, disconnect the mooring system, and take it in, and you can do this year in year out, they go, where do I sign? And that's not a joke. That is serious. Yeah, in our culture, that is probably the easiest part of the whole game.
Okay, well answered.
I don't know if it was well answered or not, but
we have a couple more questions, but maybe we could continue and save them for the end.
Good, we'll do that. So let me scroll down.
Yeah.
So now we get to the Dutch uncle part. So these are the realities. And if you're going to get involved in wave energy conversion, kind of carry this in your wallet, print it real small. Wave power is different from wind and solar. I mean, wind is interesting. I'm an aerospace engineer by training. You can make windmills and just make them bigger and bigger. And the energy recovery is related to the disk area. And you can rotate a windmill into the wind. It's nice. And then solar has its real fun part because these tiny little solar chips, you just keep making them cheaper and cheaper, make bigger and bigger panels, and it all works. Wave power doesn't work that way. It requires serious thinking. And the serious thinking is related to that Goldilocks problem. For every spectrum, there's an optimum size. And if you just wait for a certain spectrum to come in, you're sitting there waiting, and it makes much more sense to actually adjust your environment by getting these waves to crest. And a big WEC will run great in big waves, but a small WEC, but in small waves it will not move, and that is a problem that you can't get around. The small WEC can be made to work, but once you scale it up in numbers, not in size, the cost goes the wrong way. And it's not like PV cells where you can, you saw the 7 kW unit. That 7 kW unit is that size because it needs to capture waves. It needs to capture that chunk of waves to generate 7 kW. It's not like PV cells to say, now I'm going to set up a factory that pops these things out real cheap, because you can undoubtedly make them a lot cheaper, but there's a limit because there's steel that goes into it. As a matter of fact, that 7 kW unit, I don't think it actually produces as much energy in its life as it takes energy to build. Size is needed for utility level WEC, so you need to go up in size. And there's also, of course, why these windmills keep getting bigger, and the size of them is truly impressive. And as I said, the only way to build big WECs is to tune the waves. Our cost analysis, and I would love to see cost analysis from others, but it shows that only wave tuning can result in cost-effective wave energy production. And there's a Dutch Wave Energy Association Society, and not Dutch, European Wave Energy Society, and we've talked to them, and we said, we'd love to join you, but only if there is exchange of economic analyses, because we can talk about hardware till the cows come home, but if it's not economically viable, why are we doing any of this? And nothing has come out of that, and that is problematic. That's problematic for this industry. Lots of money, and I said millions and millions of euros, but also of course dollars, have been and are being wasted in systems that cannot work from an economic point of view. It simply cannot be done. Once you do the economic analysis, we need to scale it up. Can we do it? And then it becomes impossible. The ability to store energy is important. We want to have one size fits all. You think in terms of deployment, maintenance, and survival, and I really appreciate the questions on SurfWack about this, because it is a real issue that you really have to manage. And the way I'm putting it, if there's no realistic path to utility level wave energy conversion, why would anybody put money into it? Then the next truth is that wave and offshore wind should go together. It's a economic freebie, to save the overall installation cost, and that needs to be a policy consideration. Even if wave energy is not commercially available or viable right now, government agencies that provide subsidies and things like that need to press the offshore wind people in playing that game. In many ways, offshore wave energy conversion is more attractive than offshore wind. And what I mean by that is that offshore wind does run into visual pollution issues. Wave energy conversion, you won't see these things. You simply won't see them. Once we get it to work, I think we'll have a lot of happy people along the coast. And interestingly too is that offshore wind might push to stay close ashore, to not have to invest in the subsurface infrastructure, the cable. But if you force it to work with wave energy conversion, then they might move out further offshore. So actually, offshore wind becomes more attractive because it moves further offshore. Let's never forget that the triad is there, and the triad is very important. And sustainable energy is too important for snake oil. So in other words, we as engineers have a duty to look at these projects and say, hey, is this commercially viable or not? Or is this even technically viable? If it's not, let's not do it. And the engineering community needs to take the lead in that. And we have to get rid of tinkers and curbside promoters. The hope is, there is hope. And all I'm saying that SurfWack is one. And there are other systems out there that can deal with wave tuning. And I mentioned wave roller. I showed you wave roller, and I'll show you in a minute what's going on. And even beach front overtopping devices can be improved, because if you can make if you can change the bottom profile in front of the overtopping device, you can tune the waves to some extent too, although not as effectively as offshore. So this is the wave roller. This actually is an artist impression. I think it's even a little smaller than the unit that's actually been towed out. But you can see it sitting there, and it's going flippy floppy. Now, when I look at this with the experience I had with SurfWack, I go, well, that's nice, but when the tide changes, the efficiency of that flippy flopper is going to change. And when the wave heights change, you also have a different response. There's all kinds of things that take place. You basically have to have this thing, first of all, in a zero tidal environment. And secondly, when the waves get really big, that thing is just going to get knocked off its feet. And if the waves are small, it won't really move much. The solution is this: you just put it on a base, a submerged base that is controllable in height. And the chute started running. Let's try it again. There we go. And if you make that on a pivoting platform, a rotating platform, you can face into the waves too, in a wave direction, and that again enhances the efficiency of the unit. Mike planted 3 of these wave rollers on top of it. Oh, that went black. I don't know. Maybe I can play it again. Oh, there it goes. There's the rotation. Mike planted 3 of them on top because he felt that the combination of the base height and the cresting wave height would be more effective rather than having one of them. In other words, if I put one of them on it, I'd have a big base, but not a lot of actuator surface there. So that's wave roller. And please tell me where I'm wrong. Don't let it ever be like this. And some of you might recognize it is not the best possible picture, but that is, I think it was called the offshore the ocean cleanup system by Boy and Slat. Those of you who pay attention to what I say, not many, know that I'm very disappointed that this system ever had money wasted on it, because it simply has no economic viability. Anyway, this is the time for the next questions, I think. Well, there's the end slide, but go ahead. Any more questions?
Yes, we do have a lot more questions, actually. People think this is really interesting, apparently. Very good. I agree with them. Let's start with, any possibility that this idea can be applied to ships destined to the scraper as a retrofit? Scraper, sorry.
I like what I'm hearing because I like that kind of stuff. The one thing that I will say is, no, I get involved in conversion, ship conversion, all kinds of things. And when you talk about economies of scale, if you talk about economies of scale, conversions are not very useful. So if I had one series of ships, like with 1,000 Liberty ships after World War II, then I'm sure that we could think of something to make that work. The one thing that I find interesting, that I personally find interesting, is that structurally, these things are not terribly weight sensitive. So you can actually use recycled steel in building these units if there's some kind of clever production and recycling approach for it. And that's where I would go. In other words, your ships would go to scrap and they get cut up, but we cut them up in such a way that from the scrap we can build the bases, or especially the bases. Does that make sense?
Yeah, to me, it wouldn't be a straight out reutilization, but some sort of recycling.
Yeah,
Yeah.
yeah, that's conceivable. And conceivable is the term, but we have to keep in mind that with energy production, we have to be stone cold and think stone cold in the most effective production, the same way in PV solar, to some extent with these windmills, with the offshore wind, but also in car production, and all battery production. We really have to take that to the end of the production curve.
Okay. There's also a suggestion about incorporating maybe fisheries,
Right.
so floating farms.
Oh, I
Yeah.
love that part. Incorporating fish farms, it's 10 miles offshore, 130 feet of water. I'm not sure what to think about that. But what I really love is that the ocean actually underproduces. And the ocean underproduces because fish production comes from shelter. And you need to have a certain level of shelter, and then that produces fish and small fish, and then the big fish swim around, and then you build these systems. And in the United States, I'm sure in Europe too, there have been lots of artificial reef construction efforts. And these artificial reefs are remarkable how productive they are. Now, it's hard to fish right on the reef itself. You tear your nets up and all kinds of complicated stuff. But if you build these hatcheries, of course, the fish population goes up by itself. So I do think there's a very strong effect between the sustainable offshore energy generation systems, whether it is offshore wind or whether it's these surf wax and fisheries. I mean, they go together. And in the United States, we only have one offshore wind project right now, which is Block Island, which is about 100 miles from where I am, maybe a little more. And I do know that the fishermen absolutely adore those places. That's where they go that's where they go for the striped bass. They love going to the windmills. So,
Okay.
I hope that kind of makes sense. If you're going to do fish farming, you have to throw food in there and stuff. And to a large extent, it's kind of cool that you can do this. Now, one suggestion I got from somebody is that you could put servers inside a surf wag unit and make them what is called Bitcoin somethings, Bitcoin farms, right? So generates its own energy. It stores a significant amount of energy. You have plenty of cooling. I mean, because it's sitting in ocean water, right? And so you put the server farm in it with a data connection to shore. And so And the other thing that I heard about too was really funny too is, you know, surfing. I mean, talk about surfing on surfboards is really fun. So you could actually put a string of those things close to the shore without the bobbers, and have set up a nice surf arrangement.
Okay. Okay. Well, about the Bitcoin farm, the corrosion there would be a big problem.
Well, no, it's
Talk
the
about
interior. The interior of these bases is dry, right? So it's completely dry, and you may have water-cooled computers in there, and then you have you generate your own energy, and you run it to shore, and you run the data to shore.
Very good, very good. Let's see. About the SurfWack itself, is it SurfWack or SurfWack? Sorry.
Surfway. We don't care.
Yeah. Okay.
Just give us the development money. You can call anything you want to.
I'm not giving any money, but I'll call it SurfWack then.
Okay.
How is the reeling in of the wires controlled? Because snap loads need to be avoided, of course.
Right. Yeah, and this is where that neural network comes in. There's basically a big throttle valve that sits on these hydraulic motors, and so the system learns and goes, okay, well, in a certain wave spectrum, I can expect certain things, and whoa, this thing starts. I feel acceleration in the lines very quickly. Open the throttle valve, let that thing run out, and then when it comes back, I pick it in again. So as far as snap load is concerned, the snap load is controlled by the hydraulic motors, the throttle valve, and the shock absorber, the Coney shock absorber capacity in those air receivers, in those hydraulic air receivers.
Okay. And a couple of people are asking what is the limit in wave height or HS? If
I would say, and unfortunately, I'm not the person to ask that question. I would be Mike, but I would say when the waves get to be in the 20-foot range, you want to start completely submerging that bobber.
And how far does it submerge?
Well, you can lay it all the way in the bottom. You can lay the bottom and the base, and I showed that video, right? It just went down, but if it's really bad, you can lay it completely in the bottom.
Okay.
So what happens is the bobber gets flooded, and the base cranks its way down. The base is always constant tension to the bottom. Excuse me, to the bottom. So the base cranks itself down. It goes and cranks itself down and lays itself on the bottom because the pressure is much higher on the ocean floor at 130 feet. Then say 10 or 15 feet below the surface, the interior will pressurize. There's stored air cylinders, and they will pressurize the compartments that are not filled with water.
Okay. Michael Plas is asking, well, he's saying it's a good idea, Rik, but how to decide size and optimal configurations and what factors are relevant?
Right. Well, Mike has done a huge amount of work on that, and we can provide. If you're interested, just send me an email and get you in touch with Mike, and Mike can tell you more about it. But you can kind of get your head around it if you go through a thinking exercise. What you want to do is you want to say the prevalent waves offshore, I'm picking something, are a meter high, right? That's the prevalent waves. So I want that bobber to move in a meter high waves. Well, in meter high waves, the bobber is not going to move much, but because of my base, I can get that wave to crest, and I might get it to crest at 2 meters. And when that wave is crested at 2 meters and it's much steeper, that bobber is going to start moving, right? So then the question is, well, what kind of size bobber do I get to move in a 2 meter wave? And if I can get that bobber to move dynamically in that 2 meter wave, that's the maximum size for the bobber. Then when the if I were to make the bobber bigger and I generate the 2 meter wave, it doesn't move, then I'm too big. And so there's a size where it gets to be too big. And Mike has pretty much figured out that 150 feet by 150 feet size is where what you would want to have in the vast majority of ocean conditions. And we sized it specifically off New Jersey, but it works in the North Sea and it works in all kinds of places in the Caribbean, all kinds of places you come to. As a matter of fact, even places you wouldn't expect, like off Oman. So it's maybe a little less effective in the Mediterranean, and you might want to go a little smaller. But if you make these things really cheap, you're probably better off not even bothering with that. So yeah, we have done a parametric analysis and trying to find out what the optimum size would be, and the payoff is that actually in this case the optimum size is substantial, which is in the 6 megawatt, 8 megawatt range.
Is there any plan to install it somewhere?
No, we have we're looking for funding, and the weird thing is that this is not an elevator speech. I just spent an hour and a half explaining what's going on, or an hour actually, right, an hour. This is not an elevator speech, and investors need elevator speeches. And when they hear wave energy conversion, they know the amount of money that's been sunk into it, and they walk away from it. So we have a really hard time. Our initial plan is to get around $2 million to build a, I think it is a 12th scale model. And there's actually a fabulous model basin right near where we live in New Jersey that's called OMSET. And that model basin was built to allow testing of oil spill equipment. It's the only place in the United States where you make your own oil spills. And that's become a little less active as a business. And so that'd be a perfect facility where to test a 112 scale. And what's almost even more hilarious is that the 112 scale unit, if you actually pick it out at OMSET's facility and you move it about 500 meters to the north, it ends up in the Raritan Bay. And the Raritan Bay has a wave spectrum that is actually to scale of a 112 unit. So we could actually long-term test it there too. So that's our plan with $2 million to get in the first prototype in the water unit. We're talking about $20 million.
Okay, so if someone has $2 million laying around, they know.
Yeah, it's a fun science project.
Well, we have a couple of questions still, but I think we are running out of time. We've kept you for a while now.
Okay.
From my side, I would enjoy listening to you talking about it with such passion for hours. But I think people here need to have dinner, maybe there have an afternoon snack.
Good. A little cocktail too, that'd be good too.
Yeah, well, it is Wednesday, but okay.
Well, in the United States, we call that hump day. You know, you have to get through it.
Okay, true. But yeah, so this concludes our webinar for tonight. And of course, I would like to thank you, Rik, on behalf of KNVTS for taking the time to talk with us tonight. This was such an interesting topic. I really, really enjoy hearing about it. Also, thank you for all your help with the articles for our newsletters, and it's always something I look forward to reading. And when the situation is better in the world and it's possible to travel again, we would like to invite you for a nice dinner in Amsterdam. Let's hope we can do it sooner rather than later.
Thank you. My email address is there, and if the people that have the additional questions would like to have answers to them, feel free to email me, and I'll try to get them answered over the course of the next couple of weeks.
Yes, please, guys and girls. Also, thanks, Thijs, for your help on the background. Safe sailing to you for the next 4 months. Thanks, everyone, for logging in tonight. Next month, let's see if it's on the screen.
It is.
It's on the screen. Next month, we have a webinar on the approval of large composite ship elements and structures based on infracore technology. So write down on your calendar, May 19th. And as always, if you want to keep up to date about our events, you can sign up to our newsletter and check Rik's articles every now and then, and follow us on social media. That's it for tonight, and stay safe until next time. Bye.
Thank you. Good night.